Alright, so this is sort of the last video about limits before we start talking about the derivative. And so now we need a more powerful way of evaluating limits. We can't just plug in numbers and hope it's going to work for two reasons. One is it's going to get too complicated to plug in numbers, and the other reason is that we're actually going to want answers that involve variables, not numbers. And so since we're going to want answers that involve variables, we have nothing that we can plug in. And so we need a way to be able to evaluate limits when we can't plug something in. And so it's sort of easy to compute when you have a graph, and that's nice. And it's possible for me to make graphs where you can't compute the limits nicely. It's basically easy if the limit winds up being an integer, but if the limit were something like 23 195ths, you would not have a good time. And computing with calculations is labor intensive. Just plugging in a bunch of numbers, using a calculator, it takes a bunch of time. And so, suppose I told you the following thing was true for any possible number you had. The limit as x approaches a of c is c. Right? So c is a number. C could be like 5 or 30 or 82. And the limit as x approaches anything of a number is just that number. So this is a law, this is a rule. Anytime you see this limit, you can replace it with that number. Could you compute the limit as x approaches 3 of 7? Go ahead, pause the video, think about it. Now, are you done thinking about it? We just said that the limit as x approaches anything of a number is that number, so the limit as x approaches 3 of 7 should be 7. And it is. That is the right limit. Well, how about let's look at this one. What's the limit as x approaches negative 3 of pi? Well, again, pi is just a number. It's a fancy number, but it's a number. And so the limit as x approaches anything of a number is that number, which tells us that this limit is pi. One last one. What's the limit as x approaches 2 from the left of 1/2? Well, since we know the limit as x approaches 2 has to be that number, the limit on the left and the limit on the right must also be that number. Remember, the limit as x approaches 2 only makes sense if the limit on both sides makes sense. And so the limit on the left makes sense, and it also has to be 1/2. Well, that was kind of nice. We didn't have to plug anything in. Let's go ahead and look at some more rules. So here's a really important rule. This rule is the basis for a bunch of other rules later. So if I told you for all a, the limit as x approaches a of x is a, right? So what that says is if your function is just f of x equals x, then whenever you go to a, the limit is a. So could you compute the limit as x approaches 3 of x? Again, pause the video, look at what's in the box, and figure out what you should write. Now that you're back, I'm hoping what you figured out is that what you should write is 3. Right? The limit as x approaches 3 of x is 3. One more. The limit as x approaches negative 8 of x. And remember, the limit of x as x approaches anything is that thing, and so the answer should be negative 8. Nothing unexpected. Well, here's another one. For any two functions that have a limit at a, right, so if you have f of x and g of x, and the limit as x approaches a of f of x makes sense, and the limit as x approaches a of g of x makes sense, then the limit of the sum of the two functions is just the sum of the limits of the two functions. So let's see that in practice. I want you to compute the limit as x approaches 2 of x plus 3. Pause the video, try to use what's in the box plus the previous slides in order to solve this. Alright, now that you're back, let's go ahead and solve it. The previous thing tells us that if the two limits exist, it should equal the sum. So let's go ahead and write out the sum. We want the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. Now, we can only write this if those two limits exist, but thankfully for us they do. The limit as x approaches 2 of x does exist, and we see that it exists from this page, and in fact the answer is 2. And from the previous page, we see that the limit as x approaches 2 of 3 is 3. And so these limits exist, and so now we can go ahead and replace them with the appropriate answers. We get 2 plus 3, and so we get 5. And so this is how we approach limits, at least for now. What we're going to do is we're going to use the rules that we have and apply them one by one in order to break the limits into things we can just plug the answers in for, and then we move forward. So some more rules. Here we have, for the entirety of the rules that I'm going to be putting down here, f and g are functions, and both of their limits exist at a. So, here in this first box, the way you want to think about this rule is that the limit of the product of two functions is just the product of the limits. Right? Instead of multiplying the two functions and then taking the limit, you could take the limit of each functions and then multiply those answers. Here we have the power of a function. Right? We have f of x to the nth power, and the limit as x approaches a of f of x to the nth power is just the limit of f of x to the nth power. And so again, instead of taking the function to a power, you can sort of go backwards, take the limit of the function, and then take that answer, whatever the number is, and put it to that power. And just like powers, we can do roots. So instead of taking the nth root of f of x and then taking the limit as x goes to a, we can take the limit as x goes to a of f of x and then take the nth root of that. Here's a big one, and this big one comes with a qualifier. The limit of a fraction of two functions is the fraction of the limits only when the bottom limit isn't 0. And that's important. It's important that the bottom limit isn't 0 because it won't make sense as a limit. But we're going to see what we can do sometimes when the bottom is 0. And this is triple boxed. And it's triple boxed because it's one of the most important ones we're going to use the entire semester, which is if two functions are identical except when x equals a. All right, so two functions are totally identical except when we're at the point we're trying to take the limit at, then the limits must be identical. Right? And this is so important. You're going to use this to evaluate all of the limits you can't evaluate for other reasons, because you're going to find a function that's easier to talk about and easier to take the limit of than the one you're working on, so that the two functions are identical except at the limit point. And so let's go ahead and just calculate some random limits. Here we have the limit as x goes to 2 of 3x squared. Now, the way we want to think about this is that 3x squared is 3 times x squared. So the first thing we can do is write this as two limits like this. The limit as x goes to 2 of 3 times the limit as x goes to 2 of x squared. Now, go ahead and pause the video and figure out what the limit on the left is of the limit of 3 as x goes to 2. And if you're back, that should be 3. And we can rewrite the limit as x goes to 2 of x squared as the limit as x goes to 2 of x squared. And you should remember that the limit as x goes to 2 of x is 2, so we get 3 times 2 squared, and that's 3 times 4, which is 12. And so that's our limit. And how about the limit as x goes to negative 1 of x minus 5 over 2x? Remember, we're allowed to rewrite this as a fraction of two limits. First, we can write it as the limit as x goes to negative 1 of x minus 5. And on the bottom, we can write it as the limit as x goes to negative 1 of 2x. Now, we're going to do things the long way for a little bit longer, and that means writing the top as the limit as x goes to negative 1 of x minus the limit as x goes to negative 1 of 5, and the bottom as the limit as x goes to negative 1 of 2 times the limit as x goes to negative 1 of x. And I want you to take a second, pause the video, and figure out why I did that, as well as what comes next. And if you're back, we should see that the answer on top is negative 1 minus 5, and the answer on bottom is 2 times negative 1. And if we simplify, the top becomes negative 6, the bottom becomes negative 2, and you should remember that a negative on top and a negative on bottom cancel, and we get 2 into 6, which is 3. And so that's our final limit. So here's a tough one. The limit as x goes to 1 of x squared minus 1 over x minus 1. We might be tempted to do it the following way. We might be tempted to write the limit as x goes to 1 of x squared minus 1 over the limit as x goes to 1 of x minus 1. And if you pause the video and try to figure out the limits, you'll see that what that becomes is 0 over 0. Now that's bad. And the reason it's bad is, one, we can't change it into the fraction of limits if the bottom one winds up being 0. That was one of our rules. And then the other is that 0 over 0 is meaningless to us. It's unhelpful. And so what we have to do is we temporarily have to figure out another function which is the same as x squared minus 1 over x minus 1. Let's do that by factoring x squared minus 1 over x minus 1. The top factors is the difference of squares, x minus 1 times x plus 1, and the bottom is just x minus 1. Now, you may notice that there's a very strong urge to cancel the x minus 1s. And these, in fact, this function is equal to the same function, x plus 1, if, and only if, x is not equal to 1. Right? If x isn't 1, then x minus 1 isn't 0. And so we can actually cancel the x minus 1s as long as they're not 0. And so what we have, and the way you want to think about this, is if I were to graph x squared minus 1 over x minus 1, then what I'd have is I'd have a function that looks like this, where that's 1. And this dot is what happens when we cancel the x minus 1s. The dot fills in and becomes the function x plus 1. And those are identical. The only difference is that one has a missing point and the other doesn't. And so what we can do from our other rule is rewrite this, the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to the limit as x approaches 1 of the function x plus 1. And you can pause this, go back a few slides, and you'll see what this equals is 2. And so the limit as x approaches 1 of x squared minus 1 over x minus 1 is just 2. And that's our final answer. Now, one last thing. This is a slightly longer video than usual, but we're going to go ahead and talk about two more things here. One is, what happens if it's a letter instead of a number? And you can see that x squared minus a squared is the difference of two squares. And so we can factor, we can factor the top of the fraction that way, and the bottom is x minus a. And so these functions are going to be identical to just x plus a whenever x is not a. Now look back and say, why is that? Right, well, if x isn't a, then x minus a can't be 0. And if the bottom's not 0, we can cancel the top and bottom factors, which are identical. And so as long as x isn't a, it's the same as x plus a. And since the limit never lets x actually equal a, we're good. So these two limits actually are the same. The limit as x goes to a of x plus a. And if you pause the video and you go ahead and look back at the previous rules, you'll see that this winds up being a plus a, which is 2a. And so that's the limit that we want. Lastly, let me just say something really quickly about the most important theorem in all of calculus. It's not entirely true. The fundamental theorem of calculus is probably the most important theorem, but this one does a lot of the work for us, and I want you to see a picture of the work that it does. It's called the squeeze theorem, and the reason it's called the squeeze theorem is that we have two functions, f of x and h of x, and a third function, g of x, which is always between them. Right? And you can see that from f of x less than or equal to g of x less than or equal to h of x. So we have two functions which sandwich or squeeze our third function. And we have the additional property that the limit for both of those functions when we get to a exist and are the same. Well, if that's true, then the limit of g of x has to exist, and moreover, it also has to be the same as the other two. And if you look between the two functions down below, I'm going to try to draw a line that bounces around between them. And I can try as hard as I might to make the function bad, but it's going to have to head towards that same limit because the other two are squeezing it together. It only has so much room to wiggle. And so that's really it. Go back, review the video, do the homework, and I'll see you in class.